movimento e no movimento da Terra, a mão todas as moléculas, a conexão
Every year, dozens of engineering teams descend upon the Aragon Motorland circuit to take part in the International Motor Student Competition. In 2025, 42 teams signed up for the E category. Of those 42, only 23 passed the technical inspection. By the time the warm-up lap ended, only 20 remained, and of those 20, only 15 survived to complete the official 20-minute race. At this elite level, high performance comes with a high cost of entry. Most top-tier teams rely on liquid-cooled battery packs, systems that come with prohibitive development costs. Resource-constrained teams that rely on air-cooled battery packs face a staggering 50 km/h performance difference in top speed.
The existing strategy seems to be force airflow through the sides of the batteries and hope that it works. Just like slap a bunch of fans on the front and hope that passing enough airflow over the battery sides is going to do it. Yeah, our strategy is a little bit different. So the idea is, instead of having to filter the air out, what we can do instead is we can just let everything in to achieve significantly low pressure head. We're trying to primarily get the heat out of the batteries axially, and that's just because the axial thermal conductivity is so much better than the radial. I think it's like 40 to 80 times more thermally conductive. So it goes through the battery radially and then into infinity, convective infinity. And then here it goes axially. Yeah. Through our bus bar, through our thermal interface material, into our heat fin, and then finally into the environment. The silicone mats, they have exactly one purpose. I want to have airflow radially going over the batteries, but I have an issue with dust and moisture. Instead of trying to filter the air, we just make it flow past an area where we don't care if it has debris or moisture. So these isolation mats essentially force air through this middle section without worrying about dust and moisture getting to the bus bars where they could potentially cause havoc.
I kind of like what you've done here for the heat removal. It seems novel. And you know, like looking at the picture, I know it's just a concept, but the bus bar is probably a lot too thin. You have to calculate the thickness needed of the bus bar, and then you have these channels of air that you could force a fan through, and because of the aluminum wall kind of makes it, it's okay for dirty air or whatever to come by, but the heat from the bus bar will transfer to the aluminum, which will then dissipate into the air.
Airflow, yeah, it's a little bit of a Hail Mary, and you're just pushing air across the cells, and unless you have a bunch of time and money for modeling of the airflow, it's going to be tricky for you.
Issues also when you do UN 38.3 and you have a thermal event on a single cell, how to contain that event.
Taking advantage of some interesting CFD studies on cooling plates that we can custom manufacture. It starts as an aluminum sheet metal, 7.5 millimeters thick, and then it is CNC'd to have this structure on it. So the structure looks like a sinusoid. The sinusoids are 180 degrees offset, so they're all like lining up with each other, and they're missing this part and this part. We can ensure that the transfer, instead of just having a flat plate from the bus bar, we can make sure that it's much better, because this is going to have a much higher Newton number.
The whole point is to understand how much heat needs to be taken out more. Say I do conduction and I'm able to say take out 70% of the heat, then I know that 30% of the heat still needs to be taken out, which I can use conduction for. But hypothetically, if I'm able to take out 95% of the heat with conduction, we don't even need fans.
Okay. For our cooling system, we designed a ram vent that is able to actively and passively drive airflow into the pack using vehicle motion and fans. The inlet area is approximately 90,000 millimeters squared, which increases to about 104,000 millimeters squared after accounting for the angle geometry. This improves the effective airflow into the system. We've also integrated an aluminum mesh at the front, which has an aperture of 4 by 8 millimeters. At an estimated speed of 60 kilometers per hour, the system can achieve a volumetric flow rate of 1.7 cubic meters per second. The system uses 9 fans for each of the battery modules to provide forced convection to cool the system further.
I started by going through the datasheets for both the Precharger and BMS. I went over their pin connections and planned out what connections needed to be made. The pre-charge datasheet also had some example configurations which I used to start making the wiring diagram. It started with general BMS connections like cell tabs, thermistor connections, and the current sensor. We also have two main contactors, one for the positive and negative terminals of the battery. The precharger basically operates as a large current limiting resistor. When active, the main contactor is opened and current flows through the precharger. When it finishes, it closes the main contactor, allowing for full current flow to the motor. State of charge. I start off with a 250 amp draw for a couple seconds, just to emulate like that. And then I cut it for tenths of a second, and then it's 200 amps continuous. And I ran that simulation for 20 minutes, and didn't run out of power. This was then followed components to the diagram to meet the safety requirements. These included the emergency stop and service disconnect, the driver kill switch, a dedicated charging contactor, HV disconnection plan. Because the pre-charge can create a bypass around the main contactor, the HV disconnect needed to be placed in such a way that it also disconnects the pre-charger.
We're using the Orion Junior BMS2 as the brains behind our device. Thermally, the BMS should ensure that the pack never reaches above 60 degrees Celsius. Went through the configuration properties. There's a lot that had to be changed and a lot that had to be designed for. It has a set of voltage taps that carefully and precisely monitor the voltage at every segment of our battery. It also has a current sensor the main high voltage cable runs through to monitor for spikes in current. And the maximum variation between cells should be under 8 or 9 degrees Celsius. This will be done with thermistors, about 1 per 9 cells. We coded the BMS primarily for charging safety, with things like detecting when the pack hits 85% capacity and slowing the inrush of charge substantially, current limiting the pack when it gets below 15% of its charge, carefully monitoring the state of charge for any abnormalities. We are currently using a passive cell balancing approach, which means that when cells are unbalanced, with some having higher capacity than others, the excess energy from the fuller cells is diverted to ground at the request of the BMS. We have the potential in the future to use active cell balancing, which would divert the excess energy into the emptier cells instead of ground. Our BMS also has a number of pin connections that we configured, some for monitoring the thermal state of the pack, some for CAN bus communication, and others for charging related states.
So the main material is the one that holds the cells together because it has to be flexible, it has to be semi-stressed. What I can do is I can create material indices based on what our needs are. This is going to make a nice plot for me, telling me that these are the materials that you can use.
The full package is going to have the cells attached by copper bus bars. Copper bus bars are attached to the thermal interface material by compression, and then the bulkhead. We have to use 1 millimeter bus bars for the current regulation. 0.5 millimeter would overheat. We chose the particular cell type, the Mollicell 21700, for a combination of energy density, price, and modularity. In the final structure, we'll have 27 parallel sets of 16 series connected cells, held in place inside the bulkheads with silicon mats and compression. To isolate the bus bars electrically and to allow the most heat to flow out of them, we have a layer of aluminum nitride that goes between the bus bars and the bulkheads. The batteries themselves, I think, have internal resistance of a few milliohm from the cell itself. Then the connection from that to the bus bar itself, connections between bus bars, and then the connections from there to the actual motor itself. Each cell adds up to like 1 or 2 watts per cell. Due to the fact that we have a lot of cells, right? Like you only have 1 HV run, but you have so many cells, so 2 watts per cell is quite a lot actually. So I think the two main areas to try to reduce power loss would be in the cells themselves, not overheating, because as you overheat, the internal resistance goes up as well, and then the HV runs. So bigger connectors or shorter runs or both.